Hello, welcome back to RadSound FRCR Physics Series. So today we're starting another series where we're gonna discuss CT, MRI, ultrasound, nuclear medicine, and radio protection. In this series, we're not going to use the ordinary method, so everything is going to be entirely different. The method that we're going to employ in this series includes the following. So we're gonna take modality and use the same logic across all the imaging modality. So one journey, one framework for every modality. We know we have to understand the source that the patient, that when the signal is produced and the detector that will detect image formation, going to optimization and safety for every modality. So let's say we're considering the start of the X-ray. So you take the X-ray, you discuss regarding the source of that X-ray, up to the image formation and safety. So the X-ray we'll discuss into details because X-ray is very important and very common in almost every radiology department. So let's say we have X-ray tool. So this is roughly the anatomy of the X-ray tool. You got the cathode side, the other side, the main glass envelope, and also sometimes a lead lining in the outer layer. So let's say we have the cathode side. So in that part, there is filament, which boils and start to produce electrons. The electrons start to form cloud around the filament, and then after clouding, they'll start moving along the vacuum toward the anode. So as the electrons start to move toward the anode, what is happening also? So we have to understand everything into detail. Electrons are moving toward the anode, then anode will start forming something. So what is happening? Why we are using rotating anode instead of stationary one? Are we still using the stationary one? What is the importance of using the rotating anode when it comes to heat dissipation? So everything we're going to discuss into detail. So looking into the anode part, what's happening exactly around the anode part? The anode is rotating, forming something. What's happening actually? So we're going to discuss into detail at the level of the X-ray formation. Why most of the everything there is forming 99% will be converted into heat. Only 1% will form X-ray. Out of that 1% of the X-ray, how many percentage will be produced by characteristic radiation and how many will be produced by Bremsstrahlung breaking radiation? So we're going to discuss into detail. So this lecture is going to be very fascinating and entirely different from other lectures. So we'll understand what are the mechanisms for the production of the X-ray from the Bremsstrahlung, which is forming almost 80% of the X-ray produced, to the characteristic radiation, which is forming around 20%. And how are we going to optimize the produced X-ray to the patient, image formation, everything, controlling the X-ray and other filtration to make a collimation, everything. So that will help you to understand the formation of the X-ray coming out of the tube to the patient, then the X-ray hits the patient, some of the X-ray passes through the patient, absorption, attenuation, then to the image formation and protection. So to understand, let us take a look into CT. CT, we go from rotating X-ray that is rotating to a detector that will detect the X-ray produced and passes through the patient. So at the X-ray, we've got a filtration, continuous rotation, and excitation. So X-ray, so we have the patient, we have the source, then there will be signal that will be produced from the patient and will be detected by the host of detectors. So as that is happening, there will be production of signal, and those signal will be converted according to the attenuation into numerical projection data that will be used in the formation of image. So as we get that, we have our data detector detected, and then the image will be formed by conversion, series of conversion that we're going to discuss, and then everything will be converged to form from that sinogram formation into an X-ray image. And from the X-ray image, we're going to be reconstruction, you then filtered by projection, I treated for reconstruction as well as many other methods. So satiety is very important. So to understand the image or the image is formed by satiety, we have to optimize some parameters such as KBP, RA, and others. So, but sometimes while going on, we will have been exposed to radiation. So we have to know the dosages for a proper safety of the patient and ourselves. Let us look into MRI. What's happening with MRI from contrast, proton to fill, and contrast from tissue contrast formation? So MRI is different, entirely different. You got something that coming from outside. You have put inside your body. MRI begins magnetic field and radio frequency energy formation. So we got some kind of alignment of some frequencies that will interfere with the body alignment and just change some alignment of the protons and start precession forms frequencies. That will be detector signal. And then we that the patient. So we get signal formation. And that signal we will have T1, T2, PD, proton density and others, and pre-induction. So after the signal formation, we have to do certain thing to get to get the information and the image. So what is happening? What is going to happen? We'll have some coils that some will receive the information, some will send, transmit, and receive the information, and in the same at the aim that will help in the formation of the image by storing such contrast into a place called K-space, and then that K-space through Fourier transformation will be converted into image. So everything must be optimized. So optimization is very important because MRI is very critical. So we have the RTE, flip angle, and others that we must play with to have our proper image and differentiate T1 from T2. In the end, safety is very important. We have to take a look, especially heating, projectile risk, and others. So what will happen with ultrasound? Ultrasound is very easy, but still important, especially when it comes to exam. So we got transducer that will convert electric energy into mechanical and vice versa. So that transducer contains inside it a bit of crystal called piezoelectric. In that piezoelectric, we have to conversion of electric to mechanical and mechanical to electric. So that's transmission. And then a bit more at when the patient, what's happening is that with the echoes or the sound wave that will go to the patient and the echo that will come back will be detected by the machine and converted into image. So everything is just based on the echo. The echo timing gives depth and the amplitude. So such will give us understanding of where we are and then the detector. So we start with the source, patient signal, and detector. So the image will be formed. There are many different types of the image. So we can have image that will be A line, P mode, which is the most common, power Doppler, color Doppler, and others. So very important to understand the image formation. All right, is optimization important ultrasound? Definitely, yeah. So you will have to know how to optimize frequency, gain, TJC, depth, focus, PRF, and others. Hence, you understand the relationship between high frequency and depth, etc. So let us now say about something about software, which includes mechanical index, mechanical thermal exposure time, Lara, especially in obstetrics cases. So now nuclear medicine. So what about nuclear medicine? Nuclear medicine entirely different. So from radiotracer to image formation, the source of radiation is the patient, not the machine. So machine is going to help you from the image. So entirely different from everything in radiology. You have the patient who is the main source of the radiation. So traces will be given to the patient into the body, it will be localized inside the organ, and then following physiology and some metabolical changes. So now everything around the patient source. So we are now moving to the signal. So how can we detect the signal? We have our signal. What will happen? Detector will do its work. But the detector depends on the type of the procedure doing. So whether it is a gamma camera, SPECT, So the collimator that collimate the signal coming to crystal to PMT, that's a proton multiplier tools, and discrimination, passivity, detection of coincidence, line of response, and others. Everything would be converted into image in the end. So image will be formed from the different type, depending planar, PET cities, PET, and others. The reconstruction accordingly. And optimization very important because a radiopharmaceutical product you given to the patient, their activity, have time, energy window, how to detect them, very important. The next one is going to be safety. Safety is very valuable also because you're doing things without understanding how can you protect yourself and the patient while employing as low as reasonably practicable. After understanding X-ray, CT, MRI, ultrasound, you have to understand how to protect yourself, public, and do less harm to the patient via radiation protection principles, safety at every stage. Let's say you got a patient, you better identify modality, what you're doing. I'm going to do CT, MRI, ultrasound, X-ray, because some of them I know no radiation such as ultrasound. So understand what you're doing, the political effect that might happen, something that might happen as deterministic, something that might happen suddenly, depending on the dosages that you're going to give to the patient. And understand sometimes dose is not equal to the image signal. For instance, you may have image signal that is very high, but still the dose is very low. So such as X-ray optimization principles, you have to understand them, justification, collimation, filtration, and other protocols. So protect yourself, protect everyone, patients, staff, carers, public, via methods such as distance, timing, shielding, monitoring, quality assurance, checking the equipment, effective dose, estimates to custody, you know that? You'll know it. And also, justify every exposure, optimize every examination, and prevent unnecessary investigation. Thus, image quality and dose must be optimized together. So, by employing physics, learning physics taught as journey, not as disconnected, we're going to understand everything, every detail. So, in the end, every modality will understand source, patient, signal, detector, image, optimization, safety, and others. So I'm happy to have you. Stay with me, stay connected. Thank you. Remember to subscribe to our channel for the next upcoming series. Thank you.